Hi guys, this is chapter 5.3 and let's start. Okay, for the first one, this one we have to do P1V1 over N1T1 is equal to P2V2 over N2T2. Okay, so pressure is given 120, volume 3 over N1 multiplied by the temperature 25 plus 273 because we want it in Kelvin, so it's going to be 298 is equal to P2 times 2 over 1 times 298. We can cancel out the moles because it's in the same container, so it stays the same. 298 as well, it's constant. Now we just do 360 is equal to 2P2, so P2 is equal to 180. Okay, next one, same thing here, 120 multiplied by 3 over 1 times 298 is equal to P2 multiplied by 3 over 1 times 398. Now cancel. 120 times 398 is equal to P2 times 298. When we do the math on calculator, we get 120. We get 160.26, so round that off, we get 160. Okay, this one is just memorization. We show the following are true about the particles of an ideal gas. They are point masses, they have zero volume, and they move in a straight line unless they undergo collisions. Okay, molar volume of an ideal gas at 32 Celsius and 5 atmosphere pressure. Okay, for this one, we have to use PV is equal to nRT. So PV is equal to nRT. Pressure is 5 times volume is equal to, and it's molar volume, so it's going to be 1 multiplied by 0.082 times 32 plus 273, which will give you 305. So 5V2 is equal to 305 times 0.082. We get 25. So V2 is equal to 25 over 5, so 5. Okay, this one, density. For density, we have a specific rule, which is density is equal to pressure multiplied by the molar mass over R times T. Okay, pressure, we know pressure is 760 multiplied by molar mass 4 over R, which is 0.082 multiplied by 27 plus 273, 300. Okay, now do that, we get 60 by 4. Alright, my bad guys. We have to change 760 mmHg to atmospheric. So we have to divide 760 by 760. So we get 1. Sorry for this one, it's 1. So it's 4 over 0.082 by 300. We get 0.162, round that off, we get 0.16. Okay, this is memorization. One model that describes gases is ideal gas model. What does ideal gas law state? A gas is made of tiny particles with zero volume. When gas particles undergo collisions with each other, they obey the laws governing elastic collision, and the molecules have the same amount of energy, average kinetic energy at the same temperature. Okay. Next one. Okay. An evacuated cylinder fitted with a piston was filled with a certain mass of neon gas Ne at 32 Celsius. Without changing the temperature, the piston was pulled to double the initial volume. Okay. So after putting the piston inside the tube, the pressure is half the initial and the mass is the same. Okay. So mass is going to be the same. The mass is not affected because we are changing the volume. So we know that when the volume and pressure is inversely proportional. So when you double the volume, the pressure is going to be halved. So that's why the pressure is half the initial and the mass is the same. Okay, an evacuated rigid container was filled with a certain mass of a gas X at 100 Celsius without changing the amount of gas. The gas was heated to 300 Celsius. Inside the container, the pressure is greater than the initial and the mass of the gas is the same. Yes, because now there is more kinetic energy and the particles are bouncing off each other, so there is greater pressure. The mass is still not affected. Okay, this one, P1 V1, so we can do 150 times 4 over 1 times 100 plus 273, 373 is equal to 150 multiplied by volume over 1 times 473. Cancel. Okay, so now we have to cross multiply. We get, let's see, 373 times V2 is equal to 4 times 473. So divided by 373. We get 5.07 to round that off, 5.07. Right. Okay. This one, same again. 50 times 6 over 1 times 177 plus 273, which is we get 450 is equal to 100 times V2 over 1 times 627 plus 273, get 900. Cancel. We can do 1, 9, 1, 9, so 6 over 9 is equal to V2 over 9. So when you cross multiply, it doesn't change. V2 is 6. this one, we have to do P1, which is 1.2 times 3 over over 12 over CH4. So CH4 is 12 plus 4, 16. So 12 over 16 to find the moles. 12 over 16, we get 0.75 multiplied by the temperature, which is 54. Okay, 54. We'll just put T2 because it stays the same either way. We'll cross it out. Is equal to P2 multiplied by 3 over, now here it says 12 more grams of methane gas are added to the container, so it's double, so it's going to be 24 over 16, which will give us 1.5, which is the moles, multiplied by the T2. It's constant, so cancel out T2, cancel out volume. So 12 cross multiply here, so 12 times 1.2 times 1.5, get, and then divided by 0.75, we get 2.4 to 1.8 divided by 0.75 is equal to 2.4. Alright. Okay, this is PV is equal to nRT. PV is equal to nRT. So pressure, we don't know. P times volume 3 is equal to N, which is, we have to find N, 0.044 over hydrogen H2, it's diatomic, so it's 2. We get 0.022 equal to 0.022 multiplied by 0.08 times 57 plus 273, which will get us 330. So 0.022 times 0.08 times 330 is 0.5808 divided by 3, we get 0.1936. So on that off, we get 0.194. Okay, this one we're gonna have to use, we're gonna have to find the partial pressure first, which is always, actually before using the partial pressure, it's best to find the moles. We can use that to find the mass. So PV is equal to nRT. So we have 2 times 25 is equal to N times 0.08 times the temperature, 25 plus 273, so 298. We get 0.08 multiplied by 298. Okay, 50 divided by 23.4. Okay, so 50 equal to 23.84 N. N is equal to 2.1. Okay, so now that is the moles, that is the entirety of the moles, the total moles. So we know that the mole fraction is 0.5. So it's going to be, to find mole fraction, to find partial pressure, we always use the mole fraction multiplied by the total pressure. So 0.5 multiplied by 2, we get 1. 0.25 multiplied by 2, we get 0.5. Again, 0.25 multiplied by 2, we get 0.5. Okay, to find the mass, we have the moles, we have the molar mass. Now 2.1, we know 2.1 multiplied, no, 2.1 is the molar mass, what am I saying? Sorry, 2.1 is the total mole, so mole fraction is 0.5. So we have to do 0.5 multiplied by 2.1 to find helium, only helium's moles. It's 50% of the entirety of the moles. So 0.5 multiplied by 2.09 by 2.1, okay, we get 1.05. We round that, we get 1. Next one is 0.25. It's quarter of the whole thing. So it's 0.25 multiplied by 2.1. We get 0.525. Round that out, we got 0.5. Again 0.5. And now we just have to multiply the moles by the molar mass to find the mass. So it's going to be 1.05 multiplied by 4, we get 4.2. We have 0.5 multiplied 0.525 multiplied by 40, we get 21. We have again 0.525 multiplied by 20, we get 10.5. Round that off, we get 11. That's it for this one. Next one. Okay. This one, we have a number of moles. What do you want? And a temperature. Okay, this one we use PV is equal to nRT. Again, we have pressure, which is 760, and then we have the volume, which is not given. Wait, see, number of moles of nitrogen gas that occupies the volume of, yes, it is given. It is 1.46 times 10 to the power of 4 centimeter cube. Okay. And a temperature of 32 Celsius. We have an, okay. First off, we need to change everything. We need 760 to be the proper version. So 760 divided by 760, because we want it in atmospheric pressure. We have 1 multiplied by 1.46 times 10 to the power of 4. We need to make it into dm cube. So that's going to be, wait. Okay, from centimeter cube to decimeter cube, we divide by 1000. So it's going to be 14.6 is equal to n times 0.082 multiplied by 32 Celsius plus 273. So that's going to be 32 plus 273, we get 305. Now we do the math, it's going to be 0.082 multiplied by 305. We get 25.01, n is equal to 14.6. Now just divide 14.6 by 25.01. We get 0.5837 to 2 6 figures. It's going to be 0.58. Right. Okay. Same thing here. Okay. Pressure exerted by 2 moles of the ideal gas. Okay. PV is equal to nRT. Pressure, we need to find our pressure multiplied by the volume, which is 2.4, is equal to n, which is 2, times 0.082 times 17 plus 273, which is going to be 290. So we do that, we have 2 times 0.082 times 290. We get 47.56. So 2.4p is equal to 47.56. We divide by 2.4. Divided by 2.4, we get 19.81, which is 19.8. Okay. Okay, this one, we have, what do they want? They want the graph for a fixed amount of an ideal gas of a constant volume. In the graph below, the pressure is given in atmosphere and the temperature in Kelvin. So they want the fixed amount of an ideal gas of a constant volume. So when volume is constant, pressure and temperature are directly proportional. So no curve is going to be straight. It's going to be proportional. But when pressure increases, temperature increases. Next one. Right here, amount of an ideal gas at a constant temperature. Okay, at a constant temperature, pressure volume is going to be inversely proportional. So when pressure increases, volume decreases. It's opposite. So pressure, so it's going to be the first one because it's a curve that if pressure is higher, volume is going to be lower, like that. It's going to be inversely proportional. Okay. Okay, this one we use PV is equal to nRT. Pressure is 1 multiplied by volume, we don't know the volume, is equal to N, which is, we have to find N. Okay, 56 mass or molar mass. 56 divided by N2, it's diatomic, so 28, we get 2. 2 times 0.082 multiplied by 25 plus 273, which is going to be 298. So 2 times 0.082 times 298, we get 48.872. So yeah, that's it. Volume is going to be 48, and then we round off the digits, 48.9. Yes. Okay, next one. Okay, this one, P1, same rule, P1 V1 over N1 T1. So they gave us the conditions, 3 atmosphere. Okay, we'll do A first. So it's 3 atmosphere multiplied by the volume of 25. It's N1 stays the same. Okay, and from 27 to 177, 27 plus 273 would give us 300 times 300 is equal to, now if the pressure is kept constant, so that being said, pressure is 3 multiplied, the volume changed, we don't know the volume, we'll find it out, that's what they want us to find. Volume 2 over N2 times 177 plus 273 will give us 77 plus 273 gives us 450. Okay, now we just find it and cross out, cross multiply. 25 times 450 divided by 300, we get 37.5, round that off, 38. Okay. Okay, now if the volume is kept constant, so same thing, but then this time volume is constant and not the pressure. So let's say here it's going to be pressure 2 multiplied by volume 2 is constant, so 25. Cross multiply again, so 3 times 450 divided by 300, we get 4.5. Yes. Okay, this one. Okay, mass of NO2% in the sample. Okay, we have molar mass. Okay, we have everything. So first we can do PV is equal to nRT because we want to find the mass. Okay, so PV is equal to nRT. We got pressure is 0.75 multiplied by 20 is equal to N, we don't know. N times RT. What is R? R is 0.08. 0.08 multiplied by temperature, which is 300 Kelvin, already in Kelvin, so it's okay. 0.08 times 300, we get 24, and 0.75 times 20, we get 15. Okay, 15 is equal to 24, and 15 divided by 24, we get 0.625. Moles is 0.625. Okay, that's the moles. Now we need to find the mass. So mass is moles times molar mass. And NO2 molar mass is 16 times 2 plus 14. So 32 plus 14, we get 46. Yeah. We do 2 O's and 1 N. Okay. 46 multiplied by 0.625. 46 multiplied by 0.625 leaves us with 28.75. We round that off, we get 28.8. Okay, now they want the temperature. For here, we can do the P1 V1. So P1, okay, I'm gonna reset. Okay, P1 is going to be 0.75 multiplied by 20 over N1. We found it to be 0.625, the moles. Yes, 0.625. Okay, multiplied by 10 is equal to 1.25 times 10 is equal to, oh, I made a mistake here. It's 300, my bad. 300 Kelvin, yeah. 1.25 times 10 over 0.625 moles multiplied by the T2, which we don't know, we'll find out. Cross out. Okay, we have 0.75 times 20, which is 15, over 300 is equal to 12.5 over T. We cross multiply again. 300 times 12.5. Now divide that by 15, we get 250. Yes, we get T2 is equal to 250. Okay, that's it for this. Now, okay, this for fixed quantity of an ideal gas in a container of a fixed volume. Pressure is 0 atm and 0 Kelvin or negative 273 Celsius. Remember, memorize this. It's whenever it's at absolute 0, which is 0 Kelvin or negative 273 Celsius, the pressure of an ideal gas is always 0. Next one. Okay. For this one, the flask is 5 decimeter cube in volume. So the volume of the oxygen is going to take up the full space. It's going to take up the full volume, like I said before. So it's going to be 5 as well. Now partial pressure, we have 20% and 80%. Now here, like I said, they said that this means by mole ratio. So we can make it like 80%. So 80% can be 0.8 multiplied by the pressure to find the partial pressure. So we can take this 80% of nitrogen as the mole fraction. So 0.8 multiplied by 850. 0.8 multiplied by 850 gives you 680. Yes, that is the partial pressure of nitrogen. Okay, last question. Consider a gas sample composed of 70%. Okay. The average molar mass of the gas sample is, now, to find molar mass, once again, like I said, we have to take 70% as 0.7 and 30% as 0.3. Now, to find molar mass, we have to multiply the 0.7 by the molar mass. So 0.7 multiplied 0.7 multiplied by 20 plus 0.3 multiplied by 4. We're multiplying the percentage by the molar mass to find the average molar mass. So when we do that, we get 0.3 times 4, we get 15.2. Yes. Now the density of the gas sample at STP. To find density, what is density? Density is mass over volume. Now, volume when it's at STP is 22.4. So we have the average molar mass. We can do 15.2 over 22.4. 15.2 over 22.4 gives us 0.678. So yeah, 0.679. Yes, that is the density of the gas sample at STP. Alright guys, that's 5.3. We'll be uploading chapter 5.4, the last one. And yeah, that's it.